This is the first lesson in Math 126, and we're going to be reviewing, we consider what basic concepts of algebra. So just going to start here. See if we can get this all working. Yeah, so in doing math in the real world, you're going to see that it's going to be pretty messy. There's going to be a lot of mistakes. So math in the real world, don't expect to be doing everything perfect the first time. And that's why, like I said, math is usually done with paper and pencil. So, working math questions also has a little bit to tell you about life. One of the life lessons of math is it's okay to make mistakes, just like in life, but you want to strive to find the correct solution for that particular situation. So again, just like in your own everyday life problems, you're striving to find the solution that fits the situation. Math has a lot to do with that as well. When doing math problems, they can become more like reading a book or watching a movie. There's a beginning, a middle, and an end. And the middle is usually the best part of the story or a movie. So to be able to appreciate math, you have to be open to new learning, new experiences, if you will. You're not supposed to have the answers. In this class, our goal is, we're going to try to journey through a lot of different topics. Your goal is, you don't have to expect to be able to understand all this, but just be open and able to try to attempt these problems. But again, my hopes that you're, are open to what math offers and what doors it can unlock in your mind that you may not even have known they exist. So again, part of math is also, it's kind of cognitive development in your brain. It helps your brain become stronger cognitively into solving problems. So there's some hidden agendas behind math, just like exercises and things, you do certain exercises to get better at certain things. And, as you know, practice makes things all better with anything. So let's begin. So the first thing is we're going to talk about is numbers. There are 10 digits used to form numbers. Those numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the 10 digits that we use to create numbers. Depending how you arrange them, it creates different numbers. Some can be small, some can be very large. So using math symbols can become very powerful, and it opens up new ways to interact with a number. So notice that if we put a 1 next to a 2 next to a 5, we read that as 125. If I write this number, these 6 digits here, and if I place a comma in there, that comma helps us to read it. So we'd read this as 100,000. We would take a pause, and then we'd read 25. Notice how you have to understand place value a little bit, because this 100 is in what's called the thousands period. So like if I have a 125 and a bunch of zeros after it, those commas help us understand that the 125 is actually in the millions period. So we'd say 125 million, but there aren't anything else to read because the rest of the trailing zeros there's nothing but placeholders there. So when it comes to working with math, you're supposed to be somewhat familiar with the place value chart. So we have what's called the units period. This is where we kind of start out with ones, tens, hundreds. This is where most of us are at, as we mostly focus with ones, tens, and hundreds. And since you're in college, you start to trickle into thousands a little bit, because you have to pay your fees and tuitions, which can be into the thousands of dollars. Okay. But most of us, when we're buying groceries and things like that, we may be, 60, 80, 90, $100. A lot of us are in that range, unless you're just buying a bulk amount of groceries a month, and then that can kind of go up a little bit more. So things that's important to understand is, not only be able to read this number, but also to be able to break it back apart in what we call expanded form. So if I read this number, notice how we have this comma here. That means we're in this thousands period. So we would say this is 217,000, and then we would read it as 504. So the comma helps us break that apart, 217,504. Some of us have a tendency to say and. The word and is not really typically there. So you have to be careful if you're writing a check on where you put that and in a check. So check writing is kind of a lost art too, because you probably pay a lot of stuff now through digital services. You may not even write a check. So if I write this in expanded form, the 2, notice how it's in the 100,000ths place. So that 2 would read as 200,000 if I break it back apart. Plus then what we're adding to that is the 10,000ths place. Since there's a 1 there, that's 1/10,000, or we would say that's 10,000. Plus then the 7 would be in the thousands place. So we'd say 7 1,000s or 7,000. Plus then, that 5 would be in the hundreds place. So it'd be 5 100s, or we'd say 500. And then there aren't any 10s, so 0 10s, or we just put a 0 there. And then the 4. So that would be considered expanded form. So the 0 could be left out, and you can just put the +4 on the end if you wanted to. So if I want to expand this out, 5,700, we would have 5 1,000s or 5,000, plus then 7 100s, or we would say 700. Oh, got too many zeros there. So, and then there really isn't anything else, right? But you could say, no 10s and no 1s, but those zeros aren't adding any values, so they could sometimes be left off. So the equality and inequality symbols used to replace words like in texting. So, we have this is equal to, but there's a symbol that represents is equal to, and that's this symbol here. That's our equal symbol. It stands for the words is equal to. Is less than is this symbol. This is the less than symbol. Is greater than would be this symbol here. So it's important to understand which one's the less than and which one's the greater than symbol. So comparing these two numbers, we have 9 compared to 12. What we're trying to do is figure out, are they equal? If they're not equal, who's less or who's greater than? So if I have 9 compared to 12, what we recognize is 9 is a smaller value. So that would be is less than, it would be this symbol here. 9 is less than 12. Also remember, within the inequality symbol, there's some memorization tools. Some people remember the inequality symbol as an alligator. It's always going to eat the bigger value. So in this case, notice how the alligator mouth is eating the 12. So it's in the right direction. So with is greater than, the alligator mouth is actually going to be what's actually less than here. So the alligator mouth is actually going to be opening to the right. It also be considered as an arrow, which is pointing to the left. So if you look at this symbol, less than, as a mouth, it opens to the right. As an arrow, it points to the left. So depending on how you do that, it has some meaning there. How does 0 compare to 0? Well, those would be equal. How does 7 compare to 3? Well, 7 would be more than 3, so that's greater than. So in a greater than, remember, one of the shortcuts is an alligator mouth. So it's going to eat the 7, or it's going to actually point to the right. So it points to the right because pointing to the right is kind of what we call the positive direction, or getting larger. Pointing to the left is kind of getting smaller. So it's kind of got that arrow concept too. The arrow is actually more relevant as we move forward than the alligator mouth. But a lot of us had learned it as an alligator mouth. So we have those 3 symbols there that we start to get into. Something else we get into is what we call fraction math. Numbers that are not necessarily whole numbers are called fractions. Proper fractions are the fractions that are less than 1. So fractions can be expressed with 2 numbers. The numerator, or the top piece, that's a vocabulary word there, numerator, if I can spell that, it's the number that describes how many pieces the whole is divided into. Oops, that's actually the denominator. Got to read that a little bit more closely. So back that up. So what is the number that describes how many pieces it's divided into is actually the denominator. The denominator is actually the bottom number. That's what's unusual about fractions, is we actually look at the denominator before we look at the numerator. The numerator describes how many pieces are selected or taken. So that's the top value. So if I look at the fraction 1/2, we actually look at the denominator first. So if I use a rectangle, the denominator says to cut it into 2 pieces. So if I slice it one time, it's now cut into 2 equal pieces. The numerator tells me how many to take or shade. So that would represent 1/2. So 1 of 2 pieces, if you will. If I'm on a number line between 0 and 1, if I cut that space into 2 equal intervals, so this would be like halfway there and then I'm there. So that would be 1 of 2 intervals. So that's how we have 1 interval, 2 intervals. The numerator tells me to only go to that 1 interval, not to the end. So if I look at the fraction 1/4, again, we focus on the denominator first. The denominator says cut that into 4 equal pieces. So to do that, what I do is I usually cut it in half and then cut each half in half. And that now creates 4 equal pieces. And the 1 tells me how many to take, so it would be 1/4. So I take 1 of 4 pieces. So if I was doing that on a number line, I would cut it in half, cut each half in half. And so we should, if I'm starting at 0, to get to 1, I should have 4 little intervals. So 1, 2, 3, 4 movements. 4 little, sometimes we call those tick marks. 1 tick mark, 2 tick mark, 3 tick mark, 4 tick marks. So there's going to be 4 tick marks to get from 0 to 1. And the 1 tells me to just move to the first tick mark. So 1/4 would be located at that spot. And this would have been 2/4, and this would have been 3/4. And of course, 4 or the 1 would have been actually 4/4. So if I'm looking at 3/5, the 5 means to cut this into 5 equal pieces. So if this is 4 equal pieces here, I know that 5 equal pieces, I have to cut it a little bit smaller. So 1, 2, 3, 4 slices. And with fraction math, those are supposed to be identical. So if I'm sketching it, it probably don't look perfect. So the denominator again tells me how to slice it. And then what part do I take? I take 3 of the 5 pieces. So 3/5 is what that would look like. On a number line, I have to cut this into 5 equal movements. So again, you have to have basically 4 little tick marks between there because the 5th mark is going to be the 1 itself. So 1, 2, 3, 4, and then the 1 becomes the 5th tick mark. So 3/5 means I go from 0, 1, 2, 3. 3/5 would be located at this spot there. So 1/5, 2/5, 3/5. So let's see here. 1/5, 2/5, 3/5, 4/5, and then 5/5 would be back at the whole. So we have that kind of going on. So fractions have powers of 10. When they have powers of 10 as their denominator, it can be described as decimal fractions because they can easily be represented as a decimal. So for instance, we know that 0.2 is a decimal, but notice on our place value chart that if you go to the right of the decimal point, that's what we call the tenths place. So 0.2 actually reads as 2/10. So 2/10 and 0.2 are equivalent. 0.2 is called the decimal form, and 2/10 numerator denominator would be described as the fraction form. So let's say if I have 5 hundredths, the hundredths place is 2 places to the right of the decimal. So the 5 would have to be 2 places to the right of the decimal. So 0 and then 5. So remember, this is the tenths place, and then the 5 would be in the hundredths place. So that's what 5 hundredths would look like as a decimal, 0.05. If I have 0.25, notice how we go 2 places to the right. So if I go 2 places right, there's the tenths place, and then there's the hundredths place. So 0.25 would be written as 25 hundredths. So the numbers all go together, 25, and then since we're in the hundredths, the 100 would become our denominator, 25 hundredths. Notice that we have these little THs. So if you see these little THs here, that kind of tells me that we're dealing with decimal math. Notice how over here we just have S's, ones, tens, hundreds, thousands, 10,000s, 100,000s, so forth and so on. If you go to the right decimal, notice how we're dealing with these tenths, hundredths. It's got that TH sound in it, so you have to kind of pick up on that. So if I have 0.125, if I want to change that to a, oops, I got that kind of backwards there. That 0.125 should be in decimal form. So if I have 0.125 as a fraction, notice how we go 3 places to the right of the decimal, tenths, hundredths, thousandths. So notice how there's got to be a thousandths on the bottom. So we have 125 thousandths. So those are equivalent. One's in fraction form and one's in decimal form. So these is what we call decimal fractions because they can easily be converted into decimals. So decimals can also be written as a mixed number. So if I have like 2.75, I could say, well, this is 2 and 75 hundredths, like that. So those would be equivalent. If I have 5 and 3/10, notice how this is a mixed number. You could say, well, this is 5. When I say and, that's a decimal point. 5 and 3/10. 3/10 would be just simply that 0.3 there. So I can go back and forth between those. So if I gave you a decimal, I can change it into a mixed number, in this case, a fraction form. If I give you a mixed number, I can change that to a decimal. So some things to pick up on. So if I give you these types of denominators, if the denominator is a 10, that would mean to move the decimal one place to the left. If I have 100, that's 2 places to the right, I should say. That arrow's pointing to the right. So if I have a 10, 1 place to the right. If I have 100, that's 2 places to the right. So this is kind of how we can change fractions to decimals. So if I have like 17 thousandths, not 17 thousandths, I would have this 17 here. But notice how I have to move the decimal. Since there's 1,000 on the bottom, this decimal has to slide over, where here I'd actually slide it 3 places to the left. So what that's saying is the 17 should be 3 places to the right of the decimal. So this 0.017. So depending how you're doing it, so but thousandths means I should be to the right of the decimal. But if I'm doing it by hand, if you write the 17 down, you're actually moving the decimal to the left to make that happen. So that gets a little bit confusing, but in the end, it has to look right. And that does look correct. So if I have 0.0625, if I want to change it to a fraction, notice how I have 1, 2, 3, 4 places past the decimal. That means our denominator should be 10 thousandths. So our numerator is the 625, and then the denominator would be the 10 thousandths. So note that when you are 10,000 or larger, the comma does come into play when you write numbers on paper. So when do trailing zeros need to stay or go? So trailing kind of means behind. With whole numbers, they must stay, but with decimals, they can be added or removed as long as they do not affect the place value. So in 250, this 0 has to stay put. You cannot drop the 0 on that. But if I have 0.250, I could write this as 0.250, or I can even drop them both and just simply say 0.25. So those trailing zeros do not affect the place value. The 2 is still in the tenths place, and the 5 is still in the hundredths place, so that does not affect anything. So one thing they're pointing out to is, if I have 0.5, 0.50, or 0.500, notice how 0.5 would be 5 tenths, 0.50 would be 50 hundredths, 0.500 would be 500 thousandths. But notice that they all still represent the same value. So the simplest way to write that would be just simply 0.5. You don't even have to put that front 0 in there if you don't want to. Your calculator typically does, though. They like the front 0, but they will not put the trailing zeros on the end either. So this 0 would probably stay put on your calculator, but you will not see your calculator add those trailing zeros unless you do something specific to your calculator to do that. So rounding decimals. Rounding is kind of an art. So these are the steps to rounding decimals. So if I want to round 93,574 to the nearest 10, the first thing you have to do is highlight the place value that you're rounding. So I'm going to mark the 7. That's the place value that I'm rounding. The next thing you have to do is look at its number to the right. If it's a 1, 2, 3, or 4, the 7 does not change. If it's a 5, 6, 7, or 9, you have to round up to the next place value. Since that's a 4, that tells me to keep the 7 the same. So everything to the left stays put, 93,570. Anything past the number we're rounding just turns into zeros. So that would be what we have there. This is why we like to use pencils sometimes, so we can erase. So if I want to round 93,574 to the nearest hundred, what we did is we identify the hundreds place. So there's ones, tens, hundreds. So that would be the hundreds place. And if you notice when you read it, 93,574, you can say 100 when you hit that 5. So if I want to round to the hundreds place, what we did is look directly to its right, which is the 7. And since that 7 is 5 or more, what that tells me to do is round that 5 up to the next place value, which would be 6. So this becomes 93,006, and everything else becomes zeros. 600 is what this ends up with. So notice that when we round to the nearest 100, everything to the right of the hundreds place now just turns into trailing zeros. It makes the number easier to add and subtract and all of the above. So 93,600. The more you round, the easier the computations get if you're doing them. But you have to be careful of how hard you round, because you sometimes can lose the value of the number if you round too hard. So if I round to the nearest 1,000, so I have to underline the thousands place, which is where the 3 is. And to round it, that's where the 5 would come into play. So the 5 would tell me to round that 3 back up to a 4. So this becomes then 94,000, and everything else turns into zeros. So let's round into the thousands place. So if I want to round to the 10,000s place, that's where the 9 is. And then this, of course, is a 3. So that would mean the 9 would just stay put. So this would be 9, 0, 0, 0, 0. So everything behind that turns to 0. So it's just 90,000. Okay. Now, if this was, say, 97,574, if I was rounding to the 10,000s place, the 7 would have to say round on up. So notice that this actually would have to, because since you're in the 90,000s, you'd have to round up to the next thing, and that would actually be 100,000s. So that 9 would actually round up to a 10, and this would turn into 100,000. So if that was a 7 after the 9, then that actually would have to round to 100,000. Because notice that 97,000 is close to 100,000 than it is to 90,000. And that's another way to look at it. 97,574 is closer to 100,000 than it is to 90,000. So if I want to round decimals, so the nearest hundredth, so again, the hundredths place would be where this 3 is. So I underline that. And you look at its number to the right, which is a 9. So that would tell me that the 3 would have to round up to a 4. So this becomes then 54.84. Nearest 10th. So nearest 10th would be where the 8 is. And if I round that, I have to use this 3. Since that's 4 or less, that 8 would just stay the same. This would be 54.8. And again, you don't have to put the trailing zeros if you don't want to. If you want to put those zeros in, you can. A lot of times, though, they'll just drop them. So it's going to be optional. To the nearest whole number means the ones place. So to do that, we're talking where the 4 is. And we have to look at the 10th place, the 8. And that 8 would tell me to round up. So that turned into 55. So 55, and you could put a decimal point there, but you can just drop it just to say 55. That's would be the best way to write it. It's a whole number, you really don't have to put the decimal there. It's understood to be there. So next thing I want to get into is adding and subtracting. When adding and subtracting, let's start with adding numbers. Adding, you can rearrange, which is also called the commutative property. And you're allowed to group, which is using what we call parentheses. That's described as the associative property. With subtraction, though, you're not allowed to change anything. You're not allowed to group any way you want. You have to be very careful with subtraction, but addition is very, very flexible. So if I was going to add 7 plus 2 plus 8 plus 3 plus 6, what I could do is rearrange this as and put in parentheses like 7 plus 3. I could be doing this mentally. I could rearrange and put the 2 plus 8 together. And then I have this 6 goes along for the ride. So mentally, I could rearrange that problem in my head and move things around, and I'd have 10 plus 10 plus 6, which would be 26. So it allows me to add that problem fairly easily mentally if I have the ability to kind of move those things around. On the other hand, with subtraction, you have to keep it the way it is. So it's important to understand what you're starting with and what you're removing. So remember, the second number is what you're always removing. So these words like remove or take away are very important. So I'm starting with 12, and the subtraction symbol kind of means to remove 4. Okay, and it would be 8. So notice that you cannot put that in the calculator differently. You cannot say, well, 4 minus 12 and 12 minus 4. You cannot do that. So what this also means is subtract 4 from 12. So when I see this subtract 4 from 12, notice that I'm starting with actually the 12. The 12 actually goes first because you're actually taking away the 4. It has to go second. So in words, this gets a little tricky. If I say subtract 4 from 12, you cannot put that into the calculator as 4 minus 12. In subtraction, order does matter. You have to figure out who am I starting with. And the word from is important because from means you're starting there. That's what the word from means in English, is where are you from? Where are you original? This is the beginning. That's the 12. And then you're taking away the 4. So watch out for that. Don't get too big a hurry on subtraction with the calculator because order does matter. Some phrases that also represent subtraction, how many are left, how much less, how much smaller, how many more, how much larger. All those in word problems are going to be phrases that would help you understand that this is actually a subtraction problem. Subtraction using borrowing. So if I have 800 take away 225.5, to understand this without a calculator, I could break this out. So the 8 would mean 800ths. The 0 means there's no 10s, and the 0 means there's no 1s. So I can break 800 as 800, no 10s and no 1s. And if I subtract, I'm subtracting 200, I'm subtracting 20, and I'm subtracting 5. So remember, in subtraction, if we can't do that all at once, we can do it in little pieces. So notice that I can't do 0 minus 5. So what I can do is borrow, but since there's nothing in the tens place, I can't come over and borrow from the hundreds place. So I'm going to borrow 100 from there. But if I do that, that's going to be a 700. I'd have to move 100 over. We don't bring the 100 all the way over. We just slide over one place value. So that drops down into the tens place as 100. So then if I come back over here, 0 minus 5, I can't borrow anything, but I can now borrow from the tens place. So that since there's 100 there, I'm going to take a 10 from that. And that's just going to give me a 90. And then I can add a 10 over here to that 0. And this now becomes a 10. So that's what we call borrowing, is when you move over to a place value and borrow things out. So 10 minus 5 would be 5. And then 90 minus 20 would be 70. And 700 minus 200 would be 500. So it'd be like 500 plus 70 plus 5, which would be 575. So what we learn is if I have 800 take away 225, if I'm not using a calculator, in borrowing, we can't go 0 minus 5. We can't do that. So we can't borrow from the tens place. So what we do is we borrow from the hundreds place. So if I borrow 100 from there, that leaves me with 7 100s. And that comes over here, 100 would actually be 10 tens. 10 tens would be 100. So as far as tens place goes, that 100 turns into a 10 because that 10 represents how many tens are there. So 10 tens would actually be 100. And that's what we had over there was this 100. So this is kind of a little bit different language because now we're saying that 7 means 7 hundreds. This 10 means 10 tens or 100. Now I can actually borrow from the 10 and make this a 9. And then I could bring over 110, which would actually be 10 ones. And that would turn into that. So then I could go 10 minus 5 is 5. 9 minus 2 is 7. 7 minus 2 is 5, and I get 575 like that. So that's how we can subtract without a calculator. But most of us are impatient, and we just go ahead and use a calculator for that. So multiplication also means to find the product. There are typically 3 ways to write a multiplication problem. 3 times 5 equals 15 using the x. So the x symbol represents multiplication. We have 3.5, so the dot represents multiplication. We have parentheses, so if you have a number next to a parenthesis, that also means 3 times 5. And on a calculator, if you put 3 times 5 on your calculator, your display actually shows you an asterisk. 3 times 5 equals 15. So you'll see that notation using your calculator. And that's what shows up in the display. So multiplication is basically a shortcut to repeated addition. So notice how in this example here, I have like, I've got 1, 2, 3, 4, 5, 6, 7 fives. To say 7 fives, we could say 7 times 5. So 7 times 5 means 7 fives added together, which in turn turns into 35. So multiplication is a shortcut to this over here. So it's important to understand which way to write something. These are interchangeable. So if I have 3 times 4, I can also say this is 3 fours, 4 plus 4 plus 4. And that's how some people actually do 3 times 4, is they rewrite it in their brain as an addition problem, and then they just say 2 fours is 8, 8 plus 4 is 12. Or some people just have it memorized, 3 times 4 is 12. Notice here, 4 times 3 means 4 threes. This actually means 3 plus 3 plus 3 plus 3. And if we do this mentally, we have, this would be like 6, and this would be like 6, and 6 and 6 would become then 12. So mentally, we may do a little bit of grouping to do that and get the 12. Notice that the answers are the same. So what's nice about multiplication is it doesn't matter what way you put a multiplication problem into a calculator, you're still going to get the same answer. You're still going to get 12. So you can get away with 3 times 4, 4 times 3 in a calculator. It's not going to hurt you. So again, if I have 5 times 7, notice that represents 5 sevens, or I can say 7 times 5, which is 7 fives. Would you rather count by sevens or would you rather count by fives? If I'm doing it mentally, I'd rather count by fives. So it's like 5, 10, 15, 20, 25, 30, 35. I can skip count with my fives to get 35. So that's what's really cool. Even though I have 5 times 7, I can rewrite it in my brain as 7 times 5 and count by fives. And I can do that math rather quickly without using a calculator. Another thing we want to pick up on is the zero property of multiplication. 3 times 0 means 3 zeros. So it's going to be 0 plus 0 plus 0, but that's just simply 0. If I have 7 times 0, that just means 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. 1, 2, 3, 4. But 7 zeros still just adds up to 0. So really, when you multiply by 0, nothing's really happening. So what we pick up on is if you multiply something by 0, the answer is always 0. So if I multiply a decimal times 0, yeah, the answer is simply 0. If I multiply a fraction by 0, yeah, the answer is still 0. If I multiply 0 times a letter of the alphabet, which we call these variables, 0 times y, guess what? The answer is still 0. So the multiplication property is very powerful in multiplying things that we're not as familiar with. If you're familiar with multiplying by 0, 0, that takes you to that next level. Also, in multiplication, we learned that it's used to find the area of a rectangle. Remember, the area of a rectangle is area equals length times width. So if you multiply the two edges together, that is how you calculate the area of a rectangle. Now, the area itself is actually the number of squares inside the rectangle. So what we actually do is we divide the rectangle into squares and we count them. So the long way of doing this is if this is 3 inches high, then I cut this into 3 equal pieces. So it just takes 2 slices, and now I have 3 slices. So if I have 6 this way, then I have to cut that into 6 equal pieces, which I make 5 cuts for that, 5 equal cuts. And I'm not going to be perfect on this. So 1, 2, 3, 4, 5. So those are supposed to be equal. Not a really good job there of cutting that. So that's the nice thing is I don't have to be perfect with this because this is just kind of a sketch. It's not a true drawing. So if I count the squares inside there, we should see there's like 1, 2, 3, 4, 5, 6. There's 6 in that row. 1, 2, 3, 4, 5, 6 in that row. There's 1, 2, 3, 4, 5, 6 in that row. So what that really means is you're adding 6 plus 6 plus 6, which really means since there's 3 6s there, that's 3 times 6, which of course would have been 18. You also could have counted the other direction. You could have counted as you could have went this way: 1, 2, 3, 1, 2, 3. So you have these columns of threes. So if you count in columns of threes, if you're counting this direction, you have 1, 2, 3, 4, 5, 6 columns of 3. That means you have 6 threes. So that would actually be written as 6 times 3, which would have been 18. So that's why we learned, instead of counting these squares out using addition, this just turns into a multiplication problem. So that's the shortcut. A equals 3 times 6. And you just put that in the calculator and you end up with 18 squares. Now, since I gave you a unit of measurement in inches, we would say that is 18 square inches. Or we use the symbol 18 IN with a little 2 to represent square inches. So area measures the squares, and since they're in inches, we call this square inches, since we're talking squares. So another thing we want to pick up on is multiplying by powers of 10. When multiplying by 10, all we really got to do is add a 0 to the end. So the other thing is also trailing zeros determine how many 10s are present. So if I have 6 times 10, we know that's 60, but another way to do it is, since you multiply by 10, just add a 0 to the end there and just say 60. So if I have 75 times 10, notice that all you really got to do is, since you multiply by 10, is just add a 0 to the end of the 75 and you have 750. So really, I don't have to use a calculator for that. Also pick up on the 800. Also means 800 times 10 times 10. So since there's 2 trailing zeros, we're multiplying by 2 10s. 6,500 would be the same thing as 65. And since there's 2 trailing zeros, that would be also 10 times 10. So these are interchangeable. 6,500 is a shortcut, but sometimes we can go backwards and break it back apart and then put it back together in other ways. So what's nice is, if I have like the 6 times 73, this looks kind of intimidating. But what I can do is I can keep the 6 here. Instead of using a 73, what I can do is I can break the 73 apart into a 70 and a 3. So instead of saying 73, I can say 70 plus 3. What happens is this rectangle gets broken into 2 rectangles. So to find the area of this first rectangle, that's 6 times 70. So remember, all I got to do is really multiply 6 times 7, which is 42, and then add on the zeros, and that would be 420. And then 6 times 3 would be 18. So all I got to really do is add 420 plus 18. That doesn't look too hard. That's 438. So I can actually do that math. A lot of times I call that the box method. So if I'm doing it by hand, that's how it kind of starts out. If I have 52 times 34, using the area model, or what I call the box method, the 50 can be broken into 50 and a 2. The 34 can be broken into a 30 and a 4 using the expanded notation of addition there. This creates 4 little smaller boxes that we can find the area. So to find the area of this box, that's 50 times 30. But again, you can just ignore the zeros and say 5 times 3 is 15, and then add the 2 drilling zeros, which would be 1,500. And then to find the area of this box over here, that would be 50 times 4. Well, 5 times 4 is 20. 1 trailing 0 means I'd add a 0 there, and that would be 200. 2 times 30 would be, of course, 60, and 2 times 4 would be then 8. Then if we add that all together, I have this 1,500. And then 200 plus 60 plus 8 would be 268. So I'm just trying to find an easy way to add that. That looked easy. 8, 6, 7. So 1,768 would be the answer to that. So what happens is the box method becomes what we call the distributive property. So this is what we call multiplying through addition. So if I have 5 times 27, this turns into 5 times 20 plus 7. And then what we do is we multiply the 5 through the parentheses. So we could say 5 times 20 and 5 times 7. So if I go 5 times 20, remember that's 5 times 2, which is 10, and add a 0, that'd be 100. And then 5 times 7 would be 35, and then 100 plus 35 would be 135. Notice how when you do the distributive property, the math starts to go across the page a little bit. So it could kind of go in different directions here. So if I want to do 12 times 23, I could change this to 10 plus 2, and then 20 plus 3. And then we can use the distributive property, but the distributive property has got to be done twice in this case. So in doing this problem, this 10's got to multiply to the 20, and this 10's got to multiply to the 3. So let's start with that. So 10 times 20, well, that'd be 1 times 2, which is 2, and then 2 trailing zeros make that 200. And then I have 10 times 3 would be 30. And then our next move would be to multiply this 2 through 2 times 20 and 2 times 3. So if I do that, 2 times 20 would be 40, and 2 times 3 would be 6. So notice how the way I arranged it, I have like pieces going together. So I have this 200, and then I have this 70, and I have this 6, which turns into 276. Okay, so we have that going on for us if we wanted to. A lot of times we don't use these properties because we just use a calculator for stuff like this, but this is kind of the building blocks to how this is actually done on paper and pencil. So as we talked earlier, talk about powers of 10. So we learned that, if I multiply by 10, what we can also be doing is moving the decimal one place to the right. So, 5 times 10, we learned that means just add a 0. But what it also can mean is you can have your 5 with a decimal point, and 5 times 10 means to move the decimal point one place to the right. So what you do is you have to fill that in with the place value of a 0 there, and that would give me 50. So, 5 times 100 would be, of course, we know that's 500. But it also means 5 times 10 times 10. So from a decimal point of view, each time we multiply by 10, the decimal slides to the right. So I actually got to slide the decimal 2 places to the right. And then we have to fill that in with trailing zeros to make that 500. So there's 2 ways to look at that. So I can think of just, when you multiply by 10, add zeros, or if you multiply by powers of 10, a bunch of 10s, then you're moving the decimal a little bit more. So notice that 5 times 1,000, of course, would just be 5,000. But also keep in mind it means 5 times 10 times 10. So that means that my decimal point can be moved over 1, 2, 3 places. So I have to fill those 3 little spaces in with place value holders, which are zeros. And that does become 5,000. So if I have 35 times 1,000, notice that this can become then, 35 with a point, and then add on 3. Since I'm multiplying by 1,000, move the decimal 3 places to the right. And this becomes then 35 and 3 zeros. And since it's a big number, we come back with the common, call that 35,000. 18 times 100, it means I have an 18. And I can also move the decimal 2 places right if I wanted to. And that becomes then 18 with 2 zeros, and that becomes 1,800. So that math starts to come into play. So what we also pick up on is dividing by powers of 10 can be determined by moving the decimal 2 places the other direction. I could be moving the decimal 2 places to the left. So if I have 5 divided by 10, and also I have this 5, we could say 5/10, which would be 0.5. Those are interchangeable because that's a decimal fraction, if you will. But another way to do it is if you have 5 and your decimals here, dividing by 10 means the decimal's got to move to the other side. It's got to move left. And that ends up being this 0.5 that way. So if I have 2.5 divided by 100, the easiest way of doing that is recognize that you're dividing by 2 tens, since there's 2 trailing zeros there. So that means you have to move the decimal 2 places to the left. When you do that, though, this spot here has to be filled in with a placeholder, which we use zeros for that. So 0.025 becomes that. So it would be like 25 thousandths, actually. So if I have 152.3 divided by 100, or divided by 10, notice how since you're dividing by 10, this decimal just moves one place to the right, and this becomes 15.23. So if I have 1,587 divided by 1,000, notice how again you're moving the decimal 3 places to the left. So 1, 2, 3. And that would be 1.587. So that's actually a small value. So when it comes to multiplying decimals, this type of thinking comes into play. So if I have 5.3 times 6, what I can do is say, hey, this is 53 divided by 10. And then we're multiplying by 6. So 53 divided by 10 is the same thing as 5.3. So what we can pick up on those with some rearrangement and some neatness here, we can change this to 53 times 6, and then I can actually divide by 10. So in doing this, all we really got to do is multiply 53 times 6. And I'm just going to use the algorithm here. I'm not going to use the box method and all that. I'm just going to go 53 times 6. So 6 times 3 is 18. Carry my 1. 6 times 5 is 30, plus 1 is 31. So this gives me 318. But notice how you have to divide by 10. So that means the decimal's got to move over one spot. So what we learn is, if you look at, if we're multiplying by decimals, notice that there's only one number behind the decimal. So that means I have to lose one place to the left. So if I have 0.12 times 0.25, the way we do this is we actually just focus on not the decimals, but just the numbers. So I'm going to ignore the decimal and just say, well, 2 times 5 is 10. Carry my 1. 2 times 2 is 4, plus 1 is 5. Now remember, I have to add a 0 here because this 1 here is actually in the tens place. So, because we're ignoring the decimal. So 0, then we have 1 times 5 is 5, and 1 times 2 is 2. So we end up within this math here. We bring down a 0. 5 plus 5 is 10. Carry a 1. 1 plus 2 is 3. But notice how we ignored 4 decimal places. So I still got to move the decimal 1, 2, 3, 4 places over. So my final answer is actually going to be 0.03 or 0.03. So multiplying with trailing zeros. So again, notice that you can do this mentally. Remember, technology or calculator is just a tool. If you want to sharpen your brain power, it's important to be using it more involved with some of this math. So if I have 700 times 200, you should be able to see that math as just 7 times 2, which is 14, and 4 trailing zeros. So therefore, the answer is 140,000. 80 times 60, you should be able to do 8 times 6, which is 48. And since there's 2 trailing zeros, then you would have 4,800. If it goes out to the thousands place, the comma is not necessary there. So when it comes to division, there's 3 ways to write division. 20 divided by 5, use the fraction bar, 20 divided by 5, or what we call long division. Notice that what we're starting with is actually on the inside, and what we're dividing by is on the outside. So this is where it gets tricky if you're using a calculator to kind of take a shortcut. Because what we're really doing is we're actually seeing this as how many 5s does it take to get 20? In other words, 4 times 5 does give me 20. So we're starting to see this as a multiplication problem. So division involving 0. So if I want to do this, 5 divided by 0 is what? If we go backwards, we could say, what times 0 is 5. Well, when you multiply by 0, anything multiplied by 0 is going to be 0. So what times 0 is going to give me 5? Well, what's going to be not possible? So we use the words not possible, or a lot of times you'll see this word undefined. So you cannot divide by 0. This is not a workable problem. If you put that into calculator, your calculator is going to give you a division error. So there's some method actually is not workable at this time. And that's one of them, division by 0. On the other hand, if I give you this problem, 0 divided by 7 is what? What you could say is what times 7 is 0. Well, if I put a 0 there, 0 times 7, that would give me 0 because that's the 0 property, multiplication property of 0. So that answer would be then 0. So this answer would be, of course, 0. So remember, division can be done mentally if you're thinking backwards and using multiplication. So if I want to find the average, an average of a set of values is somewhere in the middle of the two of the numbers. So if I want to determine the average, all I got to do is add the values and then divide by the number of values present. So if I want to find the average of the following values, have a 92, an 87, a 66, a 76, an 88, a 95, and a 96. So notice that the largest value looks like a 96 and the smallest value looks like a 76. So it's got to be somewhere between 76 and 96 is the average. So if you don't get something between 76 and 96, we did something wrong. And since a lot of the numbers seem kind of high, I have a feeling this is going to be a lot closer to 96 than it is to 76. So to do this, what we can do is add the numbers together. 92 plus 87 plus 76 plus 88 plus 95 plus 96. So there's 1, 2, 3, 4, 5, 6 numbers there. So if I put those numbers into the calculator, so we have 92 plus 87 plus 76 plus 88 plus 95 plus 96. That gives me 534. So then my next step is, once I get that 534, is I got to then type that 534 in and divide it by the number of values, which was 6. So I said 534, didn't I? So let's see if I can fix that. 534. This is where it's tricky for me, is I have a hard time writing a lot of stuff correctly on paper, so I have to really pay attention to what I'm writing. So if I put that divided by 6 into the calculator, that gives me then 89. So notice that it is a lot closer to 96 than it is to 76. So that's how I can find an average. And again, you can use the calculator. I have made some videos on how to use a calculator here. So I'll do that on a separate video. All right. So that concludes it. But again, you can follow these steps here using a calculator, but I also made another video using the calculator to put fractions in.